activated.
Hello again. I am your AI co-host, and welcome to 3.8. 3.8 is a podcast focused on the process of doing and the process of novel invention, all from the foundation of creativity. Each month will bring you no more than 5 episodes through the lens of art, science, and/or technology. You can support this podcast at patreon.com/38. Dmitri Kalashnikov is a climate scientist and National Science Foundation postdoctoral research fellow at the University of California, Merced. Having created convolutional neural network-based predictive models for lightning in the western United States, he is currently working on applying these predictive models to climate models to project future changes in the climatology of lightning storms in the western United States. They dive into how political policies and funding cuts threaten the scientific foundation we all rely on. Dmitri breaks down the rigorous multi-year process of publishing a scientific paper and explains his groundbreaking new research that uses AI to predict future risk of lightning-caused fires. From the ostrich effect in politics to the real-world value of predicting extreme weather, this conversation reveals why the work of scientists is more critical than ever. And now the humans.
Today we're joined by Dmitri. Where does the podcast find you?
Yeah, hey Andrew, thanks for having me. It's my second time on this podcast. I was here, doing the recording shortly after the election last November. And remember, here we are now in the middle of 2025, and I'm still a postdoctoral research scientist at the University of California, Merced, and I'm still remote, so I live here in Portland, Oregon still, which I'm thankful to be able to do because I love this city. It's where I'm from. And yeah, still doing the best climate science I can despite the top level uncertainty in this country.
No, that's awesome. You're doing the people's work. It's been a little bit of time since the last podcast. I've been on a little hiatus doing some stuff that I might talk about in the future. It is interesting. It was like a few days or like a week after the election. I remember there was a bomb cyclone, so we were chatting through that. There's been a lot in the news with the legislative cycle, all these executive orders. And the thing I find is a lot in the media is I call it the talking head phenomenon. It's a bunch of people who are really far away from actual issues or actual people doing stuff, and they're giving a bunch of opinions. Can you talk a little bit or share maybe, has any of this national media cycle impacted your work, or are you seeing it in your fields? If you're not impacted yourself, have you seen any sorts of cracks in the system that I keep hearing about on one side and then the other side insists that it was all waste and it's all fine anyway?
I would say it's a good question, but I would say the biggest issue is not necessarily what the media is saying, it's what the government is actually doing.
Yeah.
First it was Doge, now Doge seems to be out of the picture maybe. But regardless, even without the sort of Elon Musk era that's now passed, the current administration is still not into funding a lot of science, especially climate science. And there have been real cuts, as I'm sure you're aware, cuts to the National Weather Service. Even though we just chatted about this week, they're now trying to hire back a lot of those folks.
Yeah.
Talk about efficiency, right? Other cuts to federal funding, that's real. That is real in terms of federal grants, which form the backbone of our research infrastructure in this country, either being cut or threatened this year. So that has real implications for scientists in this country trying to do research.
Yeah, and I don't think the American public really realize how foundational the massive amount of money we spend on science and education is. And it's really easy to look at the large numbers and say that's a massive amount of money, but the reality is it's really not. And when the grand scheme of our budget, like science funding is such a small percentage of our GDP, which is the total amount of money that we generate as a society. And I remember, I always talk about space, but I remember reading like the percentage of budget that NASA had during the 60s space race was like 5 or 8% of GDP. It was like pretty massive.
Yes.
And now it's like point something, right? And no, and like back then, 8% was quite a bit. If you look at how GDP has grown, like GDP has grown exponentially almost since the 60s. And like the amount of money that would be now would be probably almost $250 billion. And they spend almost nothing on it. Yet the amount of value that we get out of this industry is just astronomical, right? Everybody's talking about AI, right? The government has funded computer science at universities since the early ages of the internet in the 60s and 70s through the DARPA initiative, which has morphed into all this other stuff. Those are the people who developed the transformer architecture, right? So all this stuff comes out of academia. A bunch of smart people at Google left academia, did some stuff at Google, pushed it further. The technology caught up. And now we have OpenAI, I think, just raised a $200 billion secondary funding round, like it was today or yesterday or something like that. Listening to that this morning. So the amount of value is crazy. And I know you want to talk through a paper you have coming out. But I guess, can you help us understand, how does your research translate into something that impacts my life? Because I always talk about science, especially foundational stuff or the stuff that the government funds. It's like the lineman effect in American football, where you're protecting the quarterback, you're making a hole for someone to run through, big play happens, the running back, the wide receiver, the quarterback get all the fame and the glory. But the reality is you got a bunch of dudes sitting there on the line blocking. And if nobody was blocking, the quarterback gets sacked. But the second one of those people screws up, everybody's focused on that sole person for the rest of the game about how, because the quarterback got sacked. And so everybody's really important, but we have this like hero persona, single focus problem in America. And so how does the science that you're doing for lightning strikes and weather patterns and all that kind of stuff, how does that impact me, especially now in wildfire season?
Yeah, it's a great question. And before I answer that question, I want to touch real quick on what you said before that. Yeah. Yes, the sort of government public funding for science, for research, has a pretty large return on investment in this country. Mm-hmm. And also just the services that agencies like the National Weather Service or the broader National Oceanic Atmospheric Administration, NOAA, what they provide, I forget the exact numbers, but it's a massive amount of percent in terms of return on investment in economic value to this country.
Yep.
Compared to the actual dollars put in paying their salaries and whatever to do research. So it's a really important service that by the way, a lot of private weather and climate companies are also built on, the data that originally public funded. So it's important not to lose sight of that. In terms of your question about, I believe, like how or why the science I and similar climate scientists do is important to your daily life, it may not always seem super obvious. Let's say I publish a paper, which I'm about to this month, that says that the risk of lightning-caused fires will increase in the future. How is that relevant to you now or in the future? It's two-faceted, I would say. One is public awareness, knowing either what's happening now already in terms of trends actually happening, and or what's gonna happen soon. In terms of public awareness, that's important. It's good to understand what's happening to the planet. It's good to be an informed voter and citizen, etc., and maybe even make some lifestyle decisions, maybe long-term decisions. If you have asthma or something, where wildfire smoke may impact you more in certain areas than others, it might impact where you want to live in the next 10, 20 years. But even more, I would say, than that, or at least as important as that, is hopefully enacting some kind of policy changes, some kind of meaningful action and funding for that action. So if the papers I or other scientists publish get coverage, they get read by lawmakers or by constituents who then put some kind of pressure on lawmakers, and not just lawmakers, also like policy people in the management landscape of sectors that might have something to say or do about climate change. If there is conversations and discussions among those people based on the science I and others put out, then that's going to hopefully lead us to somewhere better, some kind of collective consensus that we should do something, right? Without scientific studies, it's going to be more difficult to generate that sort of credible base of knowledge to have our decisions.
Yeah, and I could speculate all day as to why I think things are happening, but it almost feels like I feel like there was a little bit of a tangent, because it's not an episode of 3-8 without a tangent. But one of the philosophical conundrum you have in trying to understand something, they call it the ostrich effect, because ostriches famously sleep with their head underground or like nap or something. I don't remember exactly.
Or don't they stick their heads underground when they're afraid? That might be like an old wives' tale. But
yeah, no, they do it. It's just, I think everybody thinks that that's what they do, but it's not a really common thing, but it's kind of what they're known for. But the idea with the ostrich effect is basically, if I don't have the data to prove me right or wrong, then it's not a problem. It's like the if you don't ask the question, then you don't really get the answer. So I feel like the administration is really cutting this stuff as like a political show to say, hey, we're removing fraud, waste, and abuse, even though there's definitely fraud, waste, and abuse in every industry, in every sector, public and private. The amount of fraud, waste, and abuse in academic sciences, I've worked in this, I know you work in this. Sure, it's there, it's like everything else, but it's such a vanishingly small amount of money, and it usually gets corrected, right? People get found out, or the waste eventually gets figured out, because everybody in the system, there's limited resources, right? Every human has this problem, and so eventually it'll happen. So I think part of it is a politics thing to get big dollar amounts for people who aren't used to big dollar amounts. And again, the amount of money we spend on science and research in this country is vanishingly small compared to anything else. But the second piece I'm really starting to wonder is that if we're not studying things, if we're not getting the data, then there's no problem, right? Like the carbon thing is such a politicized thing now, and I don't understand why. The amount of carbon going into the atmosphere is unobjectively increasing year over year. That's the data, right? You can postulate as to why. One side will tell you that it's a natural phenomenon, and the other side will tell you that humans have nothing to contribute, and the other side will tell you that burning fossil fuels obviously creates carbon, because hydrocarbons, aka oil, gas, when burned, releases carbon dioxide. I think we've talked about this on the podcast before. If you don't believe me, idle your car in a closed environment and we'll see who wins. Please don't do that. You'll die. But if you're not measuring it, then you don't have it. I guess like the practical maybe analogy on this would be, again, like you're sitting in your house on a fire. If you don't have a smoke detector and you don't have any smoke in your living room, but your kitchen's on fire, you're not going to know until your whole house is on fire. And eventually you'll figure it out because you'll observe the fire. But if you are constantly walking away from the hot door in your house and failing to open that door, you eventually get hit with the reality. And so ignorance is bliss is another way I think people have looked at this. And we're on a tangent again, but this happens a lot with like medical diagnoses, and this has been studied with all sorts of people throughout the population. Would you want to know if you were going to die, or would you want to know if you were going to get cancer? And a lot of people will be like, yeah, I want to know. I want to fight it. There's also a lot of people who would say, no, I want nothing to do with this. I want it to just happen when it happens, and I'm just going to live my life in complete unawareness of any sort of chronic condition that I may or may not have. That's fascinating to me, because I am definitely in the I want to know, and if there's something I can do to like make my life longer or make my life better or potentially even beat cancer or whatever, I would want to know that. But a lot of people don't. And so I feel like that's the movement of if we don't study the atmosphere, if we don't study weather, we're not studying this stuff, then we're just not going to know how it changes. But eventually it will change, and it is changing. And eventually that's going to be catastrophic. And we just saw floods in Texas not that long ago. Yes, it was a flood-prone area. But as we talked about, I think last time, like the probabilities of weather and shit, the 500-year flood happens like all the time now, not because it's math is wrong or science is wrong, but because of the extremes in the weather are happening more frequently, or weather in general happens more frequently. We almost need to do a video podcast so we can like draw shit, because I feel like this is all really abstract and it's hard for folks to really grasp. But when it comes to wildfires, and maybe we can talk a little bit about your paper too, because I think the wildfire thing, it's become this weird, just it's part of life. And like I've lived in the West Coast now for a long time. And when I first moved out here, wildfire, and I've lived in America my whole life, and I remember wildfire season when I was like a kid was like, it happened in the summer. There was always be some big fire. It'd make the news and it would suck, and you might get a little smoke in the neighboring area states, but like you would never really get it on the East Coast, or if you did, it was this like one couple days massive news cycle, the smoke from Canada or California or whatever is in New York City, oh my God. And now it's just like happens and everyone's just, oh yeah, it's wildfire season. So we're already seeing the impacts, but we're not able to really draw the conclusions, it seems, as a society to like how this stuff happens. And I know that's part of what you're studying. So I guess, actually, before I ask that, what is a paper? I talk a lot about it on the podcast, and I refer to a lot of them, and I read a lot of them. But I don't know if I've ever actually asked anyone who's written a paper to explain what the hell is an academic paper.
That's a great question. Yeah, I take it for granted being heads down in
right?
science.
It's like asking a fish, what is water? You're like, oh, I don't know. This
It's a good question. Yeah. Yeah. So when I and other scientists say paper, we mean a peer-reviewed, published paper in a scientific journal, right? An academic sort of outlet. So it means that we did a certain amount of analysis, right? We had our research questions, we had our hypotheses, we had data, we had to analyze the data, look for patterns, interpret results, make maps, make charts, and then we have to put together a story about what the data shows, right? In this case, the story is that lightning and the risk of lightning-caused fires will increase in the future.
Right.
So you write an introduction, which kind of summarizes the state of research about that. What have other studies shown? Why is it important that we study lightning and lightning-caused fires? That's a few paragraphs. Then you have a section about your data and methods, what data sets you used, what methods I used. So I developed neural networks. I used this climate model. I did this. I did that. I had the fire weather index. You describe that. Then you write your results, where you describe your findings. You actually talk about what your charts and maps show. You got your discussion after that. You synthesize why what you're saying and projecting is important, right? Why we should care. What are the limitations? What are we maybe not considering? Caveats, limitations, and conclusions, right? Wrap it all up. And then typically there's multiple authors, co-authors. So then I would send it to my co-authors. They would take a look at it, provide any comments, any feedback. What else can we do? Or maybe can you rewrite this section to make it more clear? So it goes through all that until finally it's ready to be submitted to a journal. So in my case, it's Earth's Future. That's the journal. It's submitted, and then it goes through peer review. And that's where the editor of the journal sends it out to 2 or 3 other experts, other scientists who are anonymous. I don't know who they are. And they take their time to go through the paper, find any flaws, right? Any kinds of room for suggestions, et cetera, et cetera. And in about a month, maybe 2 months, sometimes longer, you get the comments, the reviewer comments back. And then you got like a month to go through and address the points they raised, make changes. Or if you don't want to make that change, you think that's not necessary, you write a response saying why we're not going to make that change. That's a whole process that takes a few months until finally you've satisfied the reviewers, the paper is accepted for publication, and you get it published. You're now a year to 2 years after when you actually started doing the research. So then there is your paper that's actually published for the world to see.
How long does that take?
Yeah, it can take a year to 2 years, sometimes longer. It just depends. But yeah, a good target is 1 to 2 years, at least from the start of research.
Right.
Yeah, the actual the timeline from when you finish the research and you write the paper, you edit it, you submit it, it gets reviewed, you change it. That itself could be 6 to 12 months.
That's crazy. It's similar to in business world. You have a case study or what they'll call a white paper where you've done a project or you've done a thing, and then you put that out either for the world to see, or you use that as part of your sales process to say, we implemented this software at this company and it saved them $30 million or whatever. I think the big difference there is that on a white paper, you have to take my word for it.
Yeah, it's not peer reviewed, right?
And maybe the customer that we worked with will vouch for it, but it's not peer reviewed. And the methods, which I think are the most important part of science, a lot of times are usually opaque or not really listed. Or they bought X piece of software and saved this money, so you buy this and you'll save it. That's not necessarily true either. And I think a lot of people have a hard time understanding that it's the blueprint for what you did as well. It's theoretically, yes. I can take your paper. I should be able to reproduce what you did. I might get slightly different results because, again, you're dealing with a shit ton of variability. But I should get relatively the same analysis, or I should get very similar. And then we start talking about statistics and variance and all this kind of stuff. But
that's the idea. It's called reproduciable science. The idea is that it should be reproducible.
Whereas in the white paper, we probably don't tell you what we did. We don't tell you that we hired 1,000 contractors to do all this operations work to get this $30 million savings. We just say, oh, you bought the software and it's worked. So it's so much of a higher bar, I think, than a lot of people in society are used to actually working at. And again, it's not a perfect system. There's no perfect system.
It's not. There's bias there too.
Yeah.
There's luck. You might get 2 reviewers who are just easy. They go easy on you. Or you might get some a-holes who really want to rip apart your paper.
Yeah, or they have a thing to prove, or they just had a bad day.
Yeah.
That's an interesting process. I'd really be interested to see how the business world would change if we had to do things more peer reviewed. The closest thing I think to peer review you have in business is open source software, right? It's you're publishing the source code, everybody can see it. You do that in science too, but I think that's the only maybe the parallel there. It's such a fascinating thing. I know that, so there's a certain level of sophistication, education, understanding, whatever you want to call it, that's required to even understand these kind of papers. Like I say, I read a lot of papers. It depends on the field. I have some pretty deep knowledge in some things, but even then it's you're in pieces of computer science, for example, and AI that I don't understand. And I need to either ask people or I have a trusted network of folks I follow, or if they publish something, I'm it's probably real. But there's this other kind of idea of this preprint. Is that big in your field, where everybody's going to these preprint servers to try to not get scooped or get it out before it's gone through this formal journal process, which typically has, like you said, 2 or 3 or maybe sometimes more people anonymously able to critique and give feedback?
Yeah, that's really caught on in popularity the past few years. This idea of before the paper is actually peer reviewed and published, you yourself upload a draft, right? The same draft you just submitted to the journal, you upload it to this preprint server. And there are several different preprint servers. And then your draft is available for anyone to read and to cite. So it's nice for a couple of reasons. One of which is because now other scientists can basically have access to your work and potentially build on it months before it would have been available otherwise. So you're accelerating the science to society. And you get some citations. You yourself, from a selfish point of view, you get the visibility and the citations before the paper is even published. Right? But not everybody does that, actually. Not everybody feels comfortable with the idea of putting out your work before it's peer reviewed. For example, I personally know some scientists who don't do that, one of whom believes that before a paper is peer reviewed, it should not be put out because it might have critical flaws that haven't yet been uncovered by the peer review process, because that's the whole point of a peer review process.
Right.
To uncover any potential critical flaws, to ensure you're not publishing garbage, right?
Yeah, and there's been some cases of that. I remember probably 9 months or so ago, there was a lab in China that put out a paper about a new superconducting material that was going to revolutionize the way that magnetism worked or something like that. We were able to build room temperature superconductors, whatever the technical term is for it. It was going to revolutionize how we did computing and all this kind of stuff. It hit a little bit of a blip. And it was a big deal, and like a lot of investment was being made. And then some other folks looked at it and were like, this is really weird that they just came up with some material that no one has ever even conceived of. I think part of it was like they used AI in quotes to determine some new composition.
Huh.
And then they were super cagey about it. And the industries, a few people in the industry were like, wait a minute. And so then a bunch of academics who were either in that field or in adjacent fields started asking questions. They looked at the paper. They're like, this doesn't seem right. Then they tried to reproduce it and couldn't.
Huh.
And so I don't remember exactly what happened, but it seemed like, I think it was basically fraudulent. I think they did have a different kind of material, but the way in which the claims that they made based on what they would have had to do to make that material usable in the way that they said were not viable. There's a lot of ways to do silicon technology that you can't commercialize or would be way too expensive to put in a computer, so we don't do it, right? That's why we use sand. There's other materials that are way better semiconductors. They're also way more expensive or way harder to work with, which is why we don't use them for the most part. So I wonder too, I see a lot of I call them armchair scientists because they'll read the preprint servers and then they think that they know everything. And a lot of times I think the preprints go on to be printed and it's all good. But there's also, as you were saying, there's a much higher likelihood of either bad science getting out because of someone made an honest mistake. And that's part of science. It's like the rest of you make a claim and then other people look at it and ask questions or try to reproduce it. And maybe the claim that you made was wrong, or maybe you made a mistake. That's the whole point. There's transparency. But then it's like the double-edged sword. And sometimes people are just lying or like but that's mostly, frankly, not the problem. It's that I find a lot of times sample size is very small, and like these 6 individuals who ate salt and drank 10 beers were totally fine. Alcohol is good for you again, right? But the average person or anyone else is going to do that, and they're going to have high blood pressure and their liver is going to fail. Or they found some kind of mutant genetics person who's like able to process alcohol in ways that most people can't. Has that happened in your industry? Especially, I hear all the fraud, waste, and abuse, right? There has to be all sorts of evidence about all this fraud and waste that's happening in the system. And I would expect there to be like a lot of people making preprint claims to then not. So I guess we haven't talked about your paper. So this is the first time I'm hearing about it too. And by the time this is out, it may or may not be available, but it's out soon. So you want to just tell us a little bit about what your paper's on and what new insights that you produced?
The paper is going to come out in a couple of weeks, but like you said, it may or may not be before this podcast episode comes out. The paper is in a journal called Earth's Future, which is dedicated to climate change projections broadly, if you will. And my paper is about future projections of lightning-caused fire risk in the Western US. And it's distinct in a couple of ways. For one, there have been a lot of other papers already which have projected future risk of fires in the US. That's been done a number of times in different ways. Papers looking at things like fire weather, increasing hotter, drier conditions projected, which would lead to a general increase of fires. Other studies have looked at sort of actual projections of burned area, if you can model how much land will burn in the future based on the changing factors that control burned area. So in my case, I brought in the lightning angle, which other studies typically don't do. So lightning is a very important cause of fires in the Western US. It's not thought of as often in such a way, but it really is, especially if you go east of the Cascades, east of the Sierra Nevada in California. In a lot of the interior West, in the dry forests, pine, fir forests, it's actually lightning that starts more fires or let me rephrase that. It's lightning that burns more land. People still...
Sure.
Yeah, but it's the lightning fires that actually get going and get larger typically and burn more land.
It is that because, so one of the hypotheses I've had about a lot of this stuff is like the fires that people start are in areas in the quote unquote wilderness that people go, but there's large stretches of America that are like relatively inaccessible to people. Yeah, theoretically you could walk through, right? But no one's going 100 miles into the middle of nowhere.
Exactly.
Yeah. Okay.
Yeah, and you compound that with, if you think about a thunderstorm outbreak, you could have 100 fires start from multiple lightning strikes, and they're in remote areas that you can't get firefighters to very quickly. So before you even have some kind of coordinated suppression attack, these fires have grown to tens, hundreds, maybe thousands of acres, versus a human-caused fire by a road that the fire department can get to,
Right.
pretty quickly. That's a big part. And so because of that, we wanted to explicitly project lightning-caused fire risk. And I don't want to get into technical weeds on this podcast.
We need that picture.
Right. But we did that in a pretty novel way. I actually trained neural network-based models to predict the occurrence of lightning in climate models. That might sound confusing, but the reason why is because if you think about a typical global climate model that puts out like temperature, future wind, rainfall, it's done at a pretty like large grid size, like maybe a degree latitude, longitude.
Mm-hmm.
And one grid cell, one pixel is 60 miles on each side. And so you can't simulate lightning. It's a small process. You can't really simulate lightning at that resolution. So these typical global climate models don't act out lightning as a variable.
Maybe a dumb question, but like how big is a lightning strike? Is that a couple, like when the lightning hits the ground or goes up from the ground to the clouds, we could have that debate too. What is the, like, is that a few feet?
There, in terms of width or in terms of... that's a good question. Yeah, it's probably just a few feet. It's not very large, but it gets weirder. You have multiple ground contact points. You can have, it's called a stroke.
Oh, sure.
Where it's like a single flash, called a flash, technically. So not a strike, but the flash contains multiple strokes. And each stroke is an individual channel that makes contact with the ground.
I see.
The strokes combine into a single flash.
That's interesting. Yeah. So I think when I think of lightning and what other people probably do too, is like you see the flash, like that was a singular bolt of lightning, Zeus throwing it from the clouds sort of thing. But for the different strokes, that single flash of lightning could strike 10, 15, 30, 100 different little areas within a pretty small subset.
Yeah, it could be one or it could be 8, whatever. And they can be like half a mile apart.
Oh, wow.
Yeah.
Okay. And then, but your resolution is 60 miles. So you're looking for a few feet within this massive grid and trying to project that. How the hell do you do that?
you do it in sort of probabilistic way, if you will. So again, climate models don't even predict or project lightning. They don't even put out lightning as
because they're looking for more of the like bigger storms, like hurricane kind of stuff, precipitation, fall, that kind of stuff.
Larger features, which you can actually simulate, let's say at the scale of 60 miles. But what you can do is you can train other predictive models to take the output of the climate model. So the fields of whether it's atmospheric pressure, atmospheric moisture, wind speed, and then based on those weather fields, and when I say fields, it's just conditions. Let's say weather conditions on that day. You can predict, will lightning happen with, let's say, 80% confidence or 90% confidence or not. And you train them on historical data. So I used 28 years of actual data from the like mid-90s to 2022, train these neural network models on basically here's a bunch of weather patterns over 30 years, and I give them the ground truth labeled data. I have lightning data that tells these models, okay, on these days there was lightning, on the other days there was not lightning. What are the weather features that distinguish a lightning day from a non-lightning day, right? And then I simply set loose those trained predictive models onto the climate model data, and they predict in the climate model space which of those days will have lightning and which of those days won't have lightning.
Got it. And maybe I'll break that down a little bit. I understood it. I don't know if other people will, but I think number one, so you have 30 years of data. So that means somebody or some buddies were like collecting that data, right?
Yeah, there's actually a sensor network. It's called the National Lightning Detection Network, or NLDN. Yep. It's a privately owned sensor network, actually.
Oh, interesting.
Yeah. But they have these about, 3-4 foot tall like sensors on the ground. And they're spaced about every 100, 150 miles apart across the US. Mm-hmm. And they basically sense, they're like electromagnetic sensors that detect where and when lightning occurred.
Interesting.
And
You
they
said
report
it's private, but I'd be willing to bet that the government put money into developing that.
I bet at some point. Yeah.
Nobody's just, what if we just put sensors all over the United States for like seemingly no reason? And I suppose too, for anyone who's flown in a plane, like a lightning strike on a plane is super rare. A lot of times now, because they fly around the storm or they fly above the storm, it does happen and you'll hit turbulence and stuff. But these types of things feed into that. And so this same network of sensors that you're using to do out research is also used probably and also, I'm sure, agriculture, sporting events. I'm sure everybody's is probably pulling this data somehow. But I guess the point I'm trying to make too is, so you're building on top of that. So there's this whole other thing happening. And this is where I talk a lot about iterative development and software on the podcast. But science is also like very weirdly iterative developed in a way too. So all this data had to be assembled. It finally hit some critical mass, or someone like you was able to be like, hey, I have this idea. Oh, I can actually even try the idea because of all of this other work that people have been doing for the last 30 years. And then you use that to, in combination with the current weather atmospheric models. So then there's a whole other group of people out there building all these models on probably the same types of data sets, 30, 50, 100 years.
Yeah, lots of people building.
And so you have, we'll call it 2 layers for simplicity. And if I talk to somebody who built climate models, they're probably going to tell me all sorts of this other people involved. But you have multiple layers of abstraction, we call it in software. And then you've built a new output based on that, from what I understand, which is a lightning prediction model.
Yeah, exactly. Yeah, there's so much that could be said about that. I'll just touch on it briefly. But so when I trained the historical or the neural network based predictive models on historical data, so I had the ground truth lightning data, but my weather data to give my models the actual weather patterns on those days came from something called an atmospheric reanalysis. I don't know if we talked about this.
I don't think so, no.
Yeah, so that's actually a pretty cool tool or set of tools we have. And there's the European one, the European agency puts out. I used the one put out by NASA. It's a NASA reanalysis. It's called MERA2, which is a useless acronym. It's like modern era retrospective analysis for research and applications. Nobody cares what it's called. The actual tool is really cool. And what they do is they ingest data from all possible sources. So they have literally a weather model at the core. They run a weather model that sort of simulates or hindcasts almost the past weather every day for the past like 45 years. And they nudge it, or I shouldn't use these jargony terms, but they ingest other data sources. So they have satellite data, they feed into it, surface weather stations, actual weather stations in cities and airports, ship observations, aircraft observations. Most folks don't know, but airliners have sensors that can measure certain atmospheric parameters as they fly around the world. That gets fed into the model to make it more accurate globally. So all of that gets fed into this simulated continuous product called a reanalysis that gives you this regular grid, nice pixels across space, and it gives you data for everywhere, including in locations that don't have maybe a lot of weather stations to pull from. And so that's how I was able to build my predictive models all across the West by combining this reanalysis with the lightning data to train the models.
That's really cool. And I need to have an artist or something do like little drawings to try to illustrate this stuff, because it's such an abstract concept. I think a lot of people listen to the show have listened to me drone on about AI enough that they probably understand a bit more of this. But if you're new, that's a really hard thing. I think I'll just leave it really simple. That's a really, really, really hard thing to do. And so this model then, is the paper also publishing the model? Is that part of it? And so anyone can pick this up, or how does that work?
It's 2 papers. I actually already published the first one in November. It was about 2 weeks after we spoke last November. I published the paper that introduced these neural network based predictive models. And so in this paper that's about to come out, I'm then applying those neural network-based models to an actual climate model.
Got it. Yeah. So you had to invent the means to make it happen, so to speak. And now your paper is the validation of that and saying that it works, I assume. Otherwise, we wouldn't be talking.
And showing showing what it actually predicts if applied to the future. Right?
That's really awesome. Can you are you able to talk about how accurate it is, or what's the certainty of prediction?
Yeah, a little bit. Of course, none of science or statistics is about 100% accuracy, right? There's in a lot of cases, there's probability involved. There's some kind of percentage, in terms of accuracy or performance. So the neural network models do pretty well. Again, not to get into technical weeds, but there's this metric called AUC, which is essentially, it combines it's like accuracy, but a little better than just accuracy. Because accuracy, if you use this concept of accuracy on predictive models, it's not always accurate, ironically, right. Because you can have imbalanced data sets where you have a lot more of, for example, positives or negatives. It'll imbalance the accuracy score. It's tough to talk about this without sounding like super jargony, but basically I use this other metric that takes into account the fact that most days don't have lightning. The majority of days at the majority of locations in the West don't have lightning, right? So you got to account for that somehow. But when you do, it's still about 80%. Statistic I'm using, this metric, is about 80% good, for predicting lightning. So yeah, there's uncertainty. 20% is not so good. So,
but the alternative would be 0%, right?
Or random guessing, 50%, right? Flip a coin, right? When I say future days will have lightning, statistically speaking, about a fifth of those days might not actually have lightning. It's useful because you aggregate, you sum it up over 30 years, like I'm doing. And that'll give you a stronger statement about how things might change once you smooth out that day-to-day uncertainty.
Well, and then the application too is that, trying to tie it back to administrative policy points. So if the goal of all of these government cuts in DOGE is to make the government more efficient, the models that you're producing would do that. So instead of saying, maybe there's a fire, maybe there's not. Maybe we should deploy a plane, maybe we shouldn't. Maybe we should go put firefighters in this area, or maybe we shouldn't. Can help you get to, again, 80%. It's not perfect. Nothing is perfect, but it's way better than just trying to guess or not doing anything until there's a 1 billion acre wildfire that's threatening towns and people and power distribution and everything else.
Yeah, or worse yet, assuming no change.
Right.
It's going to be fine. No, it's good to put some number on that. 80% likely not going to be fine, or whatever.
Because I like, part of science is to push the field or the area of study forward and build on that, which is what you've done, right? You've taken the lightning data, the weather data, you've amalgamated a system to then produce a new thing, and then someone will probably come along and take your model and improve it or use it for something else. But then there's the non-scientific applications of these, where again, if we're trying to deploy the few firefighting resources we have the best we can, because the idea is you can't grow anything linearly, right? There's more fires every year. If that is in dispute, then turn off the podcast. I don't want you to listen if you don't think that's real. That's undeniable. You can argue about why it is. There's more fires every year. They're worse. They move faster. They burn more. And so how do we effectively combat those fires with the least amount of money spent or the least amount of people's time wasted or whatever, however you want to metric it? This is the stuff that directly impacts that and should make it better. It should make our spending more efficient. It should make less waste happen because we're not having somebody guess as to where these things need to go or how we should prevent or I would say like next level would be, as we're developing cities and moving people further out of urban centers, like, should we be putting houses in this area if it's super prone to lightning? Or statistically, there's always a person who's, wow, it's statistical. Okay, yeah, statistically more relevant for danger, right? This is the same thing with the flood maps, right? The flood maps are a once in 1,000 year, once in a 500 year. And again, it's statistical probability. But if you're building in a zone that is probably going to have a flood in every 50 or 100 years, maybe you don't want to build a house there. Maybe you don't want to build a city there. Or if you do, you're going to want to take more precautions. Maybe you're going to put in a dike system, or maybe you're going to put in houses on stilts. That's a thing people do on especially coastal areas that are hurricane prone.
Sure. Yeah.
So there's a lot of and I guess what I'm trying to labor on the point is that this research is really hard. I talk a lot about that on the podcast too, in that you're trying stuff that nobody's done before. You don't know if it's going to work. The best thing you can do is form a hypothesis and set some sort of a benchmark to say we either succeeded in that or we failed. And then the question becomes, do we continue to invest in that and move forward, or do you move on to something else? This is what companies do every day. Academia is really no different, right? You built a model, you had some evidence to suggest that model would work. You built the model, you published it. The next step was then let's use the model and let's see how good it actually is, or can we tune the model? So we learned that it's 80%-ish effective. We'll just high level that. How can we make it better? Can we make it 85? Can we make it 90? Should we make it 80? This is the same stuff that businesses talk about. And one of the things that drives me nuts in our current national political sphere is we pretend like businesses have absolutely no waste and the government is only wasteful, and that it's such a different world. But the reality is we're all working in this world with different constraints. It's just the difference is your research is accessible to anybody in the world who can read, and they could take it and build off of it. Whereas if you were a private company, you would probably patent this and try to sell it to people and get money from it. And you probably could sell this to people too, because it's not even, some stuff in academia has no like real widespread business value or value, but a lot of stuff does. And that's the cool thing about America. And I don't think people realize how unique that is in the world.
Yeah, and I've had startups actually email me to thank me on prior studies. Not this current one; it's not published yet. But I published a paper about 2 years ago that, and I don't know if we chatted about this last time, but I used radar rainfall data, like radar-based rainfall measurements, and zoomed in to days when lightning started fires, and really quantified how much rain can actually fall when lightning starts fires, because a little bit can fall, just not enough to make everything so wet that it doesn't burn. So I went in and put numbers on that across the Western US. And I had two different startups actually email me. One of them actually I did a Zoom call with to just like chat. They picked my brain about it. Yeah. But they were thanking me on doing this work, and they're implementing my findings in their algorithms to help improve their wildfire forecasts.
Well, that's cool.
So that is free. It's free to them. It's stuff I've done that's publicly available.
Yeah, that's an investment for everyone. That's really cool. And I guess that was one thing that I was thinking about when you were talking. The prevalence of lightning strikes is probably higher, right, over time as the climate changes and things get worse. Is that true? I can
give you an answer. Yes. Yeah. In the Western U.S., there haven't been that many studies that looked at this, but the ones that have, including mine, do point to more lightning in the future.
Sure. And I would assume that's because there's more atmospheric energy with things being hotter and drier and more extreme. And so thunderstorms are, like, for lack of a better term, bigger and more intense.
You're close. Yes.
Yeah.
Yeah. One aspect is warmer. Yeah. Warmer is good. If you want to have more thunderstorms, it'll help that process, because if you warm the lower part of the atmosphere more, you know how warm air rises, right?
Yeah. Allegedly.
Allegedly. So you'll basically have more what's called vertical instability. The air will want to rise more. And when air rises, it cools, and the moisture condenses to form clouds and rainfall and get the charge separation going. If it's vigorous enough, you get the charge separation and you get the lightning. So all else being equal, a warmer, which is also going to hold more moisture, because a warmer atmosphere holds, that's a simple physical relationship. It has more, the actual air parcels have more room to hold moisture.
Yep.
So you'll get them rising faster, and when they condense, it'll be more water. So all else being equal, that'll produce more thunderstorms. There's other complicating factors. But that's the sort of first order.
And that's interesting, because I was reading this morning, completely unrelated. I was just reading my random Andrew stuff. And I was reading an article about how turbulence in airplanes is becoming more and more violent or worse. probably because of that. They didn't really get into the atmospheric whys, but it was climate. They was just like, because climate changed. And it's like, yeah, it's like lazy reporting, but whatever. But I assume the same kind of thing is those sudden updrafts. Like anyone who's flown on a plane and hit really bad turbulence, it's terrifying. The plane can go up or down hundreds of feet.
Yeah.
Very quickly and rapidly. And when I was like a kid, I remember flying a lot and turbulence was so much worse. And it wasn't because turbulence was worse, it's because we didn't have the data to go around, or the planes couldn't go as high, or you couldn't predict it. We got pretty damn good at it, but now it seems again the way that a lot of the areas that we normally fly in are also changing now. So we found all this, what they call like smooth air, which is air that tends to be pretty stable and not updrafty, I guess. I should have a pilot on because flying is really fascinating.
It is, yeah.
But my understanding is the smooth air is like going away, right? Or it's harder to follow, and it's like I guess like on a river, right? You have a big river, you have a channel where a lot of the water is, it's really fast, and then you have these kind of side channels so you can like swim on the beach and not get swept down the river in most rivers. Similar to air, it's just really hard to see because we can't see the air, but we can see the effects of it.
And air is essentially a liquid. It behaves like a liquid, and it's studied with fluid dynamics.
Yeah,
because it behaves the same way. Yes,
that's also really fascinating. Do you have I guess maybe the better question is, what's the success rate, right, of people like who make claims or publish papers to like the reality of that being true? How do you know something's trustworthy in your field?
Yeah, it's a good question. I think in climate work, unless you're dealing with like out on a limb kind of hypothesis, it's generally pretty trustworthy. Your typical climate science paper or study is gonna be trustworthy, I think. Maybe I'm biased saying that because I'm in the field. And there have been examples when papers generated a lot of controversy. They're just wrong. That has happened. Other times, they were just a tenuous hypothesis that the media then picked up and ran with, even though the scientists in the field were like, we're not sure that's actually so solid, you all should be talking about it. One example that I think of is the whole like wavy jet stream phenomenon. Do you remember this from last decade? There was a paper that came out in 2012 by Jennifer Francis, who was the lead scientist on this. Mm-hmm. And she had this hypothesis that because of climate change, because of global warming, the jet stream itself, and jet stream being that band of strong winds in the atmosphere that drives our weather systems like low pressure systems, storms, etc., that it's getting wavier, you know? And because of that, that's leading to more extreme weather. Because when the jet stream is wavier, it's causing more extreme, like cold waves to come plunging down from the north.
Yeah, and I guess we're in that like fluidity, hard to describe via audio. So the jet stream, if you think of from like a map, if you think of a map of the Earth, it's flat. The jet stream is this band of air that goes around the globe in some sort of a pattern. That's a 2D idea, right?
Yeah, it's generally west to east, but it's kind of like imagine a rope or a string. It sort of like oscillates north-south.
And that's where you get into the wavy, in that a lot of people, I always think about it as just, it blows east to west and there's no depth, because I'm looking at the satellite map on the weather and they're showing the illustration of this like S curve kind of thing going over the United States and high, low pressure and all this shit that I don't understand. But I guess the theory for folks at home would be that that 2D picture also has a 3D dimension, and so the jet stream will come down from 80,000 feet down to 200 feet or something and bring with it all this cold or hot air. Is that kind of the idea?
To be technically correct here, the jet stream does vary in terms of height, but not by that much. Okay. It's generally maybe 25,000, 30,000, 30-ish feet up in that area. But its motions north to south are much larger than its motion vertically. So and again, I realize that there's no visual, it's a podcast recording, but if you just imagine the sort of air rushing through the atmosphere, the main channel, this jet stream, to get moved further north, instead of coming over the US, it's now coming over northern Canada. Right. So now we're south of it instead of being under it. So that would steer storms further north into Canada and away from the US, or vice versa. If it just dips south, you might get a strong storm in Texas.
And that's the wavy theory? Or that's what
Yeah,
happened.
so
Yeah,
she was
got
saying
it.
that's
Okay.
happening more. It's just happening more where it'll like curve far to the north and curve far to the south and cause weather chaos, basically. And the media liked that story. The New York
Yeah.
Times like ran with it. Other media ran with it. Just so happened this was luck, basically. But in a couple years, so 2014 and 2015, because the paper came out in 2012, but then 2014 and 2015 were both very cold winters in the eastern US. They just happened to be really cold with a lot of jet stream action where it was dipping south and dropping cold waves into the US. So it seemed maybe she's right. Maybe the scientist, Jennifer Francis, was right. With global warming, we're having these crazy jet stream actions. But then that kind of passed. And in later years, with more data available, we saw that it actually isn't happening. The later data showed that there aren't any real trends in the jet stream becoming more wavy.
Interesting.
Looked like it in the early to mid 2010s. Just
Got it.
natural oscillations.
And that is true, right? The jet stream is fairly stable, but it does move around. It's just how it...
Yeah, it varies. It could vary over a 10-year period, then swing back the other way. But if you run the data to now, it's not actually getting wavier. So that didn't prove to be a real strong hypothesis, even though it got a lot of coverage.
Yeah, let's rag on the media a little bit more. It's going to be my new hobby. But that's it. I love that because I think we were talking about this a little bit a while ago, but the whole alien thing, I'm just going to let everybody just, what is he going to talk about now? Right. Aliens and weather. There's this new interstellar object that newer. Beginning of July, there was an interstellar object that was discovered for the first time by humans, 3I-/Atlas. And it made a little bit of a splash in media. And the claim was that it is because it defies all known patterns of observation, that it can't be a natural phenomenon. And there's a paper that was put out as a preprint. A bunch of other papers have been written. There's a guy at Harvard who is really pushing this. And we were talking about this. The media, of course, went nuts with this, right? It's clearly aliens because it doesn't conform to any known pattern. One, we've only detected 3 interstellar objects that we're aware of in human history. 2, if you actually read the paper, which I did, the conclusion clearly states, we don't think this is aliens, but it merits being studied because it's so weird.
Yeah, you shared that with me. That was interesting. And you're right. And maybe just to give a little bit more context to your listeners, it's this object that was picked up by a telescope that originated outside of our solar system. So it's interstellar. Yep. It was on a weird trajectory, right? It looked like almost the way that somebody would program like a probe, like a satellite, to pass by planets, nearby planets, to observe them. It didn't look like a naturally flying object. Yep. But yeah, you're right. The study they started out with this introduction and sort of this description of how this is so weird. This could be an alien spacecraft. But then, the conclusion said, more likely with more data, we're going to find out it's a natural object and not an alien spacecraft.
Yeah, and I think part of that is like the guy who did this, I won't give him press because he wants press. But part of it is to shake the tree a little bit and make he's the founder of an institute at Harvard who studies this stuff. So he wants, of course, to get some PR for this institute that he's founded and gets money on.
Yeah, and not his first time either.
Yeah, and so it feels a lot like to me like a startup founder, like in the software world, who is trying to sell you the app that's going to solve all your problems. And there's definitely some salesmanship. They're probably not lying, but they're definitely stretching the truth as far as they absolutely could to try to drum sales and like that. So it's like we talked, I think, a little bit about science communication last time. So you have to try to generate excitement about this shit with people who have no idea what you're talking about. Aliens, of course, most people are what? Aliens are going to read that. But at the same time, it detracts from the legitimacy of science and study. And it I think, undermines trust in the system. When you have people like asteroid, interstellar, alien object thing happening, I just feel like people don't understand that enough. So I guess if you're taking away from the conversation, the folks in the media, I want to give them the benefit of the doubt and that they're trying to do the best job they know how. But as our society is progressing and we're developing so much more, this idea of a Renaissance man, like a Michelangelo, someone who can know everything humanity knows about math and art and science in their head is like not real.
No, it's not. Everything's collaborative. All of it is done collaboratively.
And it's so difficult to get a fact, because like I work in AI, right? I've worked in AI for a long time. I listen to people, even who are in AI, talk about AI. And I'm like, you have no idea what you're talking about. Or they claim to be in AI, I should say. You have no idea what you're talking about. And then I know there's people in AI, more on the math side, that I don't understand the math very well. Like I get it, but I'm not a mathematician. But the mathematicians work with the computer scientists to develop this technology that we call transformers, which is a neural net adjacent thing that brings you ChatGPT. But all the steps to get you ChatGPT as you would go on today, or Anthropic or Gemini. I don't like to. ChatGPT is the brand everybody recognizes, but I hate the company and everything about them. They're just trying to soak up all your information, folks. Rant aside, the amount of people and expertise that has to bring that to market is astonishing. And I think that's very similar to science in that all of the work you took was probably a lot of math people, a lot of atmospheric weather people, a lot of statistics people, a lot of other people to publish and validate knowledge, which then is leveled on and built on top of.
Yes, right.
And so I try to get people to be curious and push the bounds, because I think our society, it's never been easier to be fed a conclusion. And I think it's never been more wrong. The conclusions that we're fed are just so wrong because there's such an amount of nuance required to understand anything anymore that you need at least a longer form, which is why I like doing podcasts, because we get to hit the edges and we get to talk about some of the stuff where if this was a 2-minute news segment even, we would never be able to touch on any of it. It'd be Dmitri's got a new paper.
Yeah, and of course, some journalists are better than others. Some outlets, some papers are better than others at distilling the truth, even though it's a minute or 2 minutes. So I'd like to think that the majority of what we call trustworthy outlets still deliver accurate summaries of studies.
Yeah. I guess in my point, I'm on a little bit of a rant and a little bit of a tangent, but go find the paper. Go read the introduction, which usually gives you a pretty good base of understanding. Maybe you don't understand what's going on, but that's what the kind of table stakes would be, so to speak.
Yeah,
and then go read the conclusion. The stuff is, and if you don't understand it, try to figure it out. And I would be very careful in making any conclusions from that, but I don't think there's any harm in going and looking at the original research and then ask questions. Go find someone, email the authors. I'm sure you don't get a lot of random people emailing you, but you could, right? It's not hard to find to figure you out. And I'm like, hey, I'm a startup, right? I'm really interested in your algorithm or your model. That happened, right? So the people are accessible. That's part of the openness of this whole thing, which is really cool.
Yeah, I'm accessible, definitely. Yeah. And actually, some papers have what's called a plain language summary, which actually in 200 words, it summarizes the main points in layman's terms, which is nice too.
Yeah, because the jargon, we hit the jargon a lot on the podcast, especially when we start talking about weather stuff. That's part of the PhD process, is just figuring out how to talk about the shit that you do, understanding what those jargon words mean and when you apply it or when you don't.
Yeah, you got to learn it and then learn how to talk about it.
I know we barely hit on this, but what's next?
It's a good question. I don't mind discussing it in broad terms. So I'm actually working on more like heavy rainfall right now. So one study I'm doing right now actually is on how extreme short duration rainfall, when I say short, it's like 1 to 3 hour, maybe 6 hour, how those rainstorms are changing in the Western US. Are they getting more intense or not? And where? Maybe in some areas they are, in other areas they're not. Hint, that's actually what I'm seeing. Yeah. So another paper I'm working on, actually it's currently in peer review, is on how heat waves actually affect wildfires in the West. Because we all kind of like intuitively know that if it's hot and dry, it's more of a fire risk, right? But surprisingly, there haven't actually been studies which put numbers on this, like across the Western US. What's the association between heat waves and fire burned area?
Yeah, that's really interesting because, like, obviously, heat wave, dry, bad, fire. Everyone knows that. But to your point on the predictiveness of 1 or 2 degrees could be much more devastating.
There's no modeling. It's just observations. I'm looking at the past 24 years, basically, using like satellite fire data. So data about wildfires from a NASA satellite, and then temperature data, basically. And really looking at both during when a heat wave happens and also after. There's like a lagged effect after the heat wave when all the sort of vegetation is still really dry.
Oh, sure.
It just happened. And yes, actually, I'll give you a spoiler. There is a continued effect after the heat wave when more fire, more burned area.
Yeah. See, I wouldn't have intuitively thought that, but now that you say that, I'm like, oh yeah, that makes total sense.
Yeah. So we actually show that. We put some numbers on that, and we break it down by like these regions within the Western U.S., how it differs depending on where you are. Yeah.
We both live in the Pacific Northwest. It rained yesterday, which was weird. But
it was rare for early August.
Yeah, but I remember I was driving to go do some stuff, and I was looking around and to maybe illustrate this point, right? It's been pretty dry and pretty hot, pretty normal summer, I think. Grass is brown here for the most part if you don't water, and it was raining pretty much all day on and off here. And I remember thinking about all the people's grass that is still brown and it's going to still be brown. And like thinking about the heat wave and the effects of that, it's like we had a really, I don't know, I would call it a bad heat wave, but it's been dry this summer. Everything is crispy. You get some rain. That doesn't mean it just overnight becomes green and fine again, right?
It's going to be a lot of rain. Yeah.
Yeah. So it's really interesting to think about the lingering effects and like how long do those effects, and because I could see some people saying, no shit, Dmitri, fire is worse when it's dry and there's no moisture. Why study that?
Sure.
But that's how you build that basis to get to those other questions to say, yeah, of course it's dry is bad, but how dry is bad, or how long are those effects present for, which
and then, how much does fire increase? Is it double the fire? Is it 5 times the fire? It's useful to have that information.
Yeah, to try to and then you'll put it out and someone else will build on that. And again, with the jet stream thing too, we all assume the jet stream was really wavy probably because that's what it looks like on the weather. Did a study, turns out actually no. And that's a win for science, right? We ruled something out, which is just as valuable oftentimes as ruling something in. That's proving something.
Ruling something in. Yes. Both are valuable. Yeah. Absolutely.
I always like to finish up with, is there anything that I should have asked you that I didn't?
That's a good question. I should have remembered you asking that question last time and been like ready to write a note about what you have.
Like a 2-hour dissertation to the follow-up. This is just off the top of my head, but
no, I don't think so. We covered a few things. I think pretty well. Yeah. No, I can't really think of anything right now as far as what you could have asked, but you didn't.
Is there anything that you're reading or consuming that you think other people might be interested in? This could be related to weather. This could be, I've had people talk about like TV shows that they found are interesting. I always like to try to like propagate stuff that people are doing.
Yeah. Another good question. What can I talk about without ruffling feathers maybe?
Yeah.
Although maybe what's the harm in that? Yeah, one book I recently finished is called Doppelganger by Naomi Klein. Interesting book. It was just published 2 years ago, which, given all the happenings in the past couple years, is actually a little bit outdated. But she did a deep dive into sort of the effects of social media on why we're here as of 2023. Why we're here as a country so polarized, so fractured, how the pandemic played into that, how some of the nonsense brokers out there operate. And also, quick aside, the reason why the book is called Doppelganger is because there's another Naomi called Naomi Wolf. I don't know if you're familiar with.
I've heard of her, yeah.
Yeah, and Naomi Klein is an up-and-up liberal academic researcher. She's not involved in any kind of weirdness. But Naomi Wolf is a former liberal who about 10 years ago went hard right and became like a darling of some of the far, like Steve Bannon likes to have her on his podcast because she's this former feminist liberal who saw the truth and joined the right because she now wants to like whatever spread vaccine misinformation. So anyway, the funny thing is Naomi Klein, the original one, gets confused for Naomi Wolf all the time.
Oh, shit. Yeah.
Yes, because they're both like Naomi's, they're both like one syllable last names. So people will tweet out like, what's Naomi Klein thinking? And she's, that's not me, it's Naomi Wolf. And so the book is called Doppelganger because she deep dives into that also and how it mirrors some ways our society kind of like doppelgangs itself. I mean, if that's a word. But anyway, interesting book. I recommend it.
That's awesome. Yeah, no, I've talked a lot about how social media has ruined our society on the podcast. It's been a while though. Maybe Nathan and I will talk about that this week because maybe I'll tease. I don't know if this is going to come out before or after. It's really how fast I can edit it and what I choose to spend my time on. But yesterday, which was August 6th, I'll date it, the Citizen Lab director gave a talk at Black Hat, which is a cybersecurity conference. It's pretty famous now, but the talk was on, I read this a couple days ago and I haven't seen the talk yet, but how the authoritarian ideals of governments are starting to seep into the cybersecurity industry and become weaponized against the users or the citizenry in ways that everybody's probably heard of 1984. I don't know if they've read it.
Definitely heard of it.
Yeah. So that those types of things are starting to become more and more common. And on the right, you hear this about social media and Twitter and Facebook censoring people and whatnot. But the reality is that the people on the right are using the same technologies for what most people would consider authoritarian. I know that's a political word now, but it's the government is trying to repress the citizenry. That's anti-democratic and anti-American. And I'm okay calling that authoritarian.
Sure.
We fought a war about it. If anybody actually reads American history, like that shouldn't be controversial, right? They're literally Revolution War. This thing happened, 1776. A bunch of people got mad at an authoritarian leader and said no more, never again.
Sure.
And the rest is history. But anyway, so I'm hoping that gets out soon. And if you haven't, let me try to, I get in this habit. I try to do the links after and I always forget. And so then I try to say it now in the thing so people are interested in it. Keynote was Chasing Shadows, Chronicles of Counterintelligence from the Citizen Lab. And
is that on YouTube or elsewhere? I can just pull it up.
I hope so. It literally happened yesterday at a Black Hat conference, so you have to attend it. They typically put this stuff out or they'll put stuff out. So I'm hoping within the next week or so it'll be available. But the person's name is Ron Deibert, Deibert, if folks are interested in. And I think, if you're not familiar with Citizen Lab, they do some really interesting research. I believe it's University of Toronto. And it's one of these weird kind of like public-private institutes where they I think are funded by the government of Canada or however the education system works there. But then they do a lot of really interesting analyses and study with private industries as well. They'll oftentimes partner. And so I'll tease that, but I don't look forward to talks very often. But this is one of those things where I hope the talk surfaces. There's been a couple PR pieces about it, so I'm assuming that it will. But if not, maybe I'll have them on and we can talk about it on the podcast.
Cool. And I'll look for it too. I just made a note to myself to search for it in a week after hopefully it's posted.
I appreciate you coming on and always happy to have you. Let's publish some more papers and we can talk about them.
Sounds good. Thanks for having me. It's always fun.
You can find us at 38.com. It's like the word create, but with a 3 instead of the C. As always, we encourage you to listen, watch, do. We'll see you next time. You can support this podcast at patreon.com/38 or at ko-fi.com/38. Thanks for listening.